Hello, Chemistry 11 Honors. This is Mr. Chad. And what I wanted to do today was we are going to start focusing on the gas unit in the 11 Honors. But what I wanted to do was just do a brief introduction to some of the background before we explore the gases in detail. Now, recall in grade 8 that there are 3 states of matter: solid, liquid, and gases. And according to the kinetic molecular theory, all matter is composed of particles in continual motion. And science uses the KMT to try and explain why the states of matter have their unique characteristics. Now, you have this little diagram here where you have states of matter, you have solid, liquid, and gas, and then we have plasma. Now, notice on the bottom it says add heat. So what you have here, you can think of it, is solids, the particles have low energy, while gases basically have high energy. Okay, and when you add heat to it, what you're doing is adding energy to the particles. Now, what's the significance of adding this energy to the particles? Well, if we take a look at this, one thing you will notice is that if we take a look at this column called the interparticle forces. Now, what is interparticle forces? Is the force of attraction between particles. Now, one thing you should notice is when you take a look at a solid, liquid, or gas, notice the interparticle forces for solid is very strong, liquids is average, gases are minimal. Okay, now this interparticle forces, the strength of it determines whether it's solid, liquid, or gas, because the stronger the attraction between the particles, what happens is that they are closer together, and as a result, they are not able to move as much. That's why you take a look at the particle movement. Notice for a solid, you have a very strong particle force. Notice the particle movement is generally vibrations. For liquids and gases, notice you have more random motion because the attraction between the particles is a lot smaller. Now, the increase in energy from solid to liquid to gas contribute to the decrease in the interparticle forces. So why is that occurring? Is because when objects are heated, the extra energy that's placed into the system is used to excite the molecules so that they break we call it now the intermolecular bonds, or the bonds between molecules. Now, here I use the term intermolecular bonds. It's the same idea as the force of attraction between the particles. Now, this breaking of bond results in the object going through different phases from solid to liquid to gas. Now, we have this phase diagram where we have on the y-axis, you have temperature, and on the x-axis, you have time. And recall from the introduction, what's happening is at these plateaus, what you have is you have your phase changes. Okay. Now, and in this case, this is where the energy is being absorbed to break the intermolecular bonds, or the bonds between the particles. So if I were to show you what it sort of theoretically looks like, if we do the heating curve, now notice what happens is during the gas to liquid or liquid to solid, you will notice there's a combination of solid and liquid to gas. So why does the plateau exist in those areas is because all the energy that's being added, what happens is used to break the intermolecular bonds. And so all that energy being absorbed to break the bonds results in a constant temperature. Okay? Now, one thing that you should be aware of is what you get sometimes in heating and cooling curves is you don't get this perfect flat line. Sometimes in some curves, you will see something like this. It's actually a little bump before it reaches the plateau. This is where you can have something called superheating. And what happens is that it's superheating. What happens is you actually get a higher boiling point than what is actually normal. Now, there is a reason for that, and it's due to the fact something called nucleation, which I can explain more if you come and talk to me. But what you can do is you can watch a video, okay? I'll put it into the description box below where you see how water can be superheated, okay? Now, when you talk about phase changes, solids to liquids, the kinetic energy of the particles increases. The particles are moving faster. What happens is this kinetic energy of the particles increase, weakening or even breaking some of the intermolecular bonds and allowing random motion. Okay? Now, one term that you should be aware of is something called the normal melting point. The temperature at which the solid enters the liquid states at sea level. So when you say normal melting point, basically it's solid entering the liquid states at sea level. That's what we call normal melting point. Now for liquids to gases, again, more energy is added, but now it's used to break or overcome any attractive force and escape from the liquid phase. Okay? Now, when we talk about liquids to gases, there's actually two definitions. And remember, we had talked about this back at the introduction to matter. So if we talked about, let's see, matter, okay. If you look back at your notes for matter here, let me see if we have one more. Nope. Oh, here, sorry. So we look for matter introduction. Oopsie, matter notes. Okay. Remember we talked about phase changes here? And remember I talked about boiling and evaporation and the difference between the two? Okay. So I'm just revisiting that right now. Is if you take a look at the difference in evaporation. So evaporation are particles that enter the gas phase and escape near the surface. The key word is near the surface. So in this case, what you're doing is for evaporation, you're going from liquid to gas at the surface. Okay. Now, in this case, because the high energy particles escape, the average kinetic energy of the remaining particles decrease. In other words, the temperature of the remaining liquid decreases. Now, you can think of it like this. Example, you remove all the A students, the class average decreases. Okay, so what happens is in evaporation, you have all the high energy particles at the surface, they escape. What happens is the remaining particles have a lower average energy. So what that means is over time, it takes longer and longer and longer for a substance, for a liquid to evaporate. Now, we contradict that to boiling. What is boiling? Boiling is the temperature at which the gas phase occurs throughout the liquid and forms bubbles and is able to escape. So basically, the particles have enough energy, not only at the surface, but throughout the entire liquid. Now, boiling occurs most frequently at the heat source because that's where the particles are able to obtain the most energy to enter the gas phase. So this is why when you boil water, you will notice the bubbles form closest to the heat source. And that is because at the heat source, the particles are able to get the most energy to break the bonds to go from a liquid to a gas state. Now, again, just like normal melting point, normal boiling point is the temperature at which the liquid boils at sea level. Now, what does the term boil mean? It means that they have enough energy to break the bonds to form a gas at atmospheric pressure. Now, if the pressure increases, then it will take more energy to produce enough gas to escape the liquid state. So what happens is if there's a higher pressure, then it takes more energy before the water actually boils. Now, you might think of this, some of you might say, well, where do we use this? An example would be, let's say your Instapot. Now, why is Instapot able to cook so quickly is because it is a pressure cooker. And so what happens is when you close the lid on a pressure cooker, it traps the steam, increases the pressure. Now, what happens then is the water has to go to a higher temperature to form the bubbles. Now, so what you can do is there is a video that I will, again, put the link in the description box, and it talks about the science behind the pressure cookers. So you can watch that and they can explain what's going on with that. Okay. Now, because heating requires energy, it is considered to be an endothermic reaction. To go from solid to liquid to gas, you're absorbing energy, so therefore it's considered to be endothermic. Conversely, when cooling off a substance, okay, whoops, this is not from reverse, from here, whoopsie, from gas to liquid to solid, because energy is given off, the reactions are considered to be exothermic. Again, this should follow the law of conservation of energy. Now, gases are considered to be in random motion and are constantly colliding with different objects, like the side of a balloon. And the pressure exerted is determined by the number of collisions, as well as the size or magnitude of the impact of the collisions. So when we talk about pressure, gas pressure is determined by the number of collisions, how many particles are colliding, as well as the energy of the collisions. Okay, and that's what magnitude or size of the impact of the collisions. So it says here, one can change the pressure by changing the temperature, thus changing the speed, energy of the gas particles, or changing the volume of the container. We can increase or decrease the pressure by changing the volume of the container. Now, pressure is defined as the force exerted per unit area of surface. So pressure is equal to force divided by area, which is mass times acceleration all over the area. And you see the units that are provided. okay? And when we measure pressure, there is a few units that we can use. We can either use something called millimeters of mercury, or another term is torr, kilopascals, or atmospheres, or PSI. Okay, PSI is pounds per square inch. So this is the relationship between those numbers. Okay, 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torrs, which is 101.3 kilopascals, or 14.7 psi. Now, all of these represent the same thing. All of this, all these numbers, all represent sea level. Okay. Now, how did we get this 760 millimeters of mercury? Is actually experimentally determined. And here again, I do have a YouTube link that explains how they got the 760 millimeters of mercury, and I'll put this link in the description box. Now, when we measure pressure, there are 2 different pieces of equipment we can use. One of them is a barometer, which measures atmospheric pressure, okay? And how they do it generally is to measure the height of how far a liquid goes up a inverted tube. Another one is called a manometer for general gas pressure. In this particular case, when you have a manometer, you're comparing it to an atmospheric pressure. So in this case, if we have mercury in between 2 gases, one is opened up to the atmosphere, and you notice the height of the mercury is exactly the same, then the gas pressure is equal to the atmospheric pressure. Here in this case, what you will notice is there's a difference in height. And in this case, because there's an imbalance in height, and you notice that the gas side is higher than the atmosphere side, then we know that the gas is a little bit less than atmospheric pressure. How much is measured by the height of the millimeter of the mercury, and this is how we get 710. Conversely, when the gas pressure is more than the atmospheric pressure, you will notice a difference in height in the mercury, and you will notice one side, the atmosphere height is higher than the gas pressure height. And so what that tells you is that there's a higher gas pressure than atmospheric pressure. And this is how we determine that the gas pressure is 810 millimeters of mercury. Okay. Now, this is basically the introduction to gases. The next lesson I will talk about, we'll be talking about the different gas laws. All right, folks. Thank you very much. Have a good day. Bye-bye.